Welcome. This video is going to start looking at ways to interrupt equilibrium. Remember, a system in equilibrium is at balance, but that balance can be disrupted. And it was LeChatelier who realized that changing conditions can affect the equilibrium in predictable ways. And in fact, when a system is subjected to change or stress, it's going to respond in such a way as to minimize the effect of the change. So this means whatever's done, the system usually responds in the opposite way. If you add something to the reactant side, you're going to end up making more product. If you add something to the product side, you're going to end up making more reactant. So often we use color to identify which way a system is shifting. So there's really a limited number of changes that you can make to reaction and still have the same reaction without actually changing your chemical reaction. So these changes are called stresses, and each of these stresses will likely increase or decrease collisions more on one side of the reaction than the other. So the reaction increases, we say, in that direction. For example, if you increase collisions on the reactant side but not on the product side, you're going to make more product and you're going to shift the equilibrium to the right. So as this happens, a new equilibrium is established with a different composition, meaning the concentration of your reactants and products will both increase, right? Think about it. If you add reactant, that concentration increased, it's ultimately going to make more product, so that concentration increases, but you end up with the same equilibrium constant because when it gets back to equilibrium, even though the concentration of both reactant and product increased, the ratio is going to be the same. So what are these stresses? You can change the concentration of either a product or a reactant. You can change the pressure of a reaction vessel, and you can either do that by increasing or decreasing pressure with a constant volume, or you can change volume to change the pressure. And the last stress is to change the temperature. So let's look at changes in concentration. These are the simplest to understand, I think. And again, if you think of equilibrium about having a teeter-totter with equal weight on each side, completely balanced around the center, we are shifting the balance on that teeter-totter. So if the concentration of any component increases, so you add more reactant or more product, that side of the reaction will immediately have more collisions, and the equilibrium is going to move away from that side or move toward the other side. So increase a reactant, more products produced. Increase a product, more reactants produced. The other thing you could do is you could decrease a concentration or remove either a reactant or product as it's produced. When you do that, that side of the reaction immediately has fewer collisions, and now the equilibrium moves toward that side. So if you decrease a reactant, more reactant will be produced, or if you decrease a product, more product is produced. Generally, remember, in industry, we're trying to favor the forward reaction, so the technique used in industry is often to increase a reactant or to remove a product. So let's take a look at it. We have N2 plus 3H2 forming ammonia. Remember, this is the Haber process. And so you notice that at this point, it starts out that the reaction's at equilibrium. Concentration of neither of the reactants nor the product is changing. And then H2 was added. Okay, so you see that it's dumped in. That's why it took no time. It just, boom, they dumped a bunch of H2 in. And as soon as they do that, the H2 begins to decrease, as does the N2, because they are going to have more collisions with the increase in H2, and that means more product starts to form. Eventually you come back to equilibrium, and the N2 and H2 have different concentrations. The NH3 has a different concentration, but our Kc value will remain the same. And then if we remove the NH3, which is done here, as soon as you remove the NH3, suddenly there's fewer collisions on the NH3 side, so some of the reactant starts replacing it, and we see a decrease in those two reactants as they start making more product on the other side. So this graph clearly shows the effect of adding a reactant or removing a product. Predicting changes in equilibrium with changing pressure or temperature is a little trickier, and that's because if you change a product or reactant, you're clearly changing one side of the reaction to create either more collisions or fewer collisions on that side. But when you change the pressure or the temperature, you have to remember you are changing that pressure and temperature on both sides of the reaction. It's one system. Your reactant and product are in the same container. So this means both sides will either be more crowded or less crowded because of the change in pressure, the change in temperature. And it's your job to figure out if one side will see a greater increase or decrease with that change. So the key to predicting changes in equilibrium when you change the pressure or temperature is to know which side, if either, is going to be affected more by the change in pressure or temperature. So let's look at changes in pressure. And I'm going to talk about changes in pressure. Assume it's on a fixed volume. And remember, you could change the volume to change the pressure as well. And the effect would be the same. So reactions involving gases are the only ones that will be affected by pressure changes or volume changes. So if there aren't any gases, pressure, that's easy. There's no change in equilibrium. If there are gases involved, it is going to affect both sides of the system, but it will affect the side of the system with more moles of gas to a greater degree. So if you increase pressure on a fixed volume, it's going to add more stress and cause more collisions on the side of the system with more molecules. And that means your equilibrium is going to shift in the direction that has fewer molecules or fewer moles of gas. If you decrease the pressure, same thing. It's going to have a greater effect. So you're going to see a greater decrease in collisions on that more crowded side. So the system will move in the direction that has more molecules or more moles of gas because it had the greater decrease. So let's look at an example of this. My first equation here, I've got CO plus 2H2 gives me CH3OH, methanol. So I've got 3 moles on this side that are gas, and they're being converted to just 1 mole of gas on the other side. So if I increase the pressure, I'm going to see a greater increase in collisions on my reactant side, which I should actually draw that as an arrow up, I suppose. So I'm going to see a greater increase in collisions on this side. Not that I won't see an increase in collisions on the product side as well, but I'll see a greater increase on this side. So I guess I could draw it like that to show it's greater. And that means my equilibrium is going to shift toward the product side. If I decrease the pressure on this, by the same reason, I'm going to see a greater decrease in collisions on the reactant side because it was more crowded to start with. And I'll see less of a decrease on the product side, so that means it will shift toward my reactant side. In the second equation, because I have 2 moles of reactant and 2 moles of product, it doesn't matter that it's 2 separate substances. It's just total number of molecules there. Remember, gaseous molecules take up the same amount of space. So in this case, pressure increasing or decrease is going to affect both sides equally, and we're going to see no change in equilibrium. Changes in temperature are a little easier, I think, to think about, because even though a change in temperature affects both sides of the system, every change in temperature will affect equilibrium because the reaction is either endothermic or exothermic. And you can really think of heat then as being a reactant in the case of an endothermic reaction or a product in the case of an exothermic reaction. In endothermic reaction, the reactants are favored by more energy, the products are not. And in the case of an exothermic, the products gain more of a benefit from adding energy than the reactants. So you really can think about gaining or losing, adding or taking away a reactant or product. So if you increase the temperature and it's exothermic, you can think of it as adding product. You're increasing collisions more on the product side and your equilibrium shifts left. Endothermic would be just the reverse of that. It'd be like adding reacting or increasing collisions more on the reactant side and shifting your equilibrium right. And decreasing temperature would have the opposite effect. So with temperature, you have to know if it's endothermic or exothermic, and then realize if you're increasing or decreasing, if you're adding or subtracting reactant or product. Remember, changes in temperature also are going to change Kc, however. So if we look at the first example here, at 273, I have a Kc value of 1300, and when the temperature increases to 298, the Kc value decreases. And that means I actually made less product to get a smaller ratio there. So my equilibrium has shifted left. So that leads me to believe that adding temperature is like adding a product, and this reaction is exothermic. If I look at my second example here, as I increase temperature between the second and third, or first and second and third, I see an increase in my Kc value here. So that means more product is being produced and my equilibrium shifting right. So I can assume temperature is like adding a reactant, or it's endothermic. Just a couple last things on temperature. Most reactions are naturally exothermic. The natural direction of many reactions is exothermic. So that means a decrease in temperature would favor your forward reaction, which seems like a good thing because decreased temperature costs less to do. But it means you're going to have a slower rate. Temperature always increases rate, regardless of whether it's endothermic or exothermic. So decreased temperature is cheaper, you make more product ultimately, but you make it slower. And depending upon the natural reaction rate, it might be a lot slower. Higher temperatures, on the other hand, favor endothermic reactions, but this can be problematic too. For one thing, it's going to cost you more. And another issue is, in the case of automobiles, it's the endothermic reaction that causes all the pollution and smog. Engines run hot enough that nitrogen and oxygen gases can actually combine. Usually, we can't get nitrogen in the atmosphere to combine with oxygen because it's simply not hot enough. But when you produce NO from the nitrogen and oxygen, that quickly converts to other toxins that contribute to acid rain and smog. So car companies are constantly seeking ways to lower the temperature of combustion to avoid this endothermic reaction. Last thing to talk about is adding a catalyst. A catalyst is not a stress because it does not affect the equilibrium position. It does not change the yield. It affects the forward and the reverse reaction in equal amount. So a catalyst isn't included in the calculation of Kc because it's chemically unchanged at the end of the reaction. Its concentration is exactly the same. Sometimes a catalyst is shown over the arrow. When you have the arrow drawn, it might indicate heat, or it might say H2 or Fe, indicating what that catalyst is. But remember, it affects the forward and reverse reactions equally, so it only increases the rate. So why mention them here? Well, because the whole job of a chemist in industry is to come up with a high yield of product as quickly as possible. So you want lots of product and you want it quickly. Since low temperature often favors the yield and costs less, that would be great if you could find a catalyst that would improve the rate, because you're going to lose rate by using those low temperatures. So again, yield and rate often work against each other, so it's the chemist's job to decide which is more favorable. How fast a rate do you need versus how high a yield? So you're looking for that compromise. How much temperature do you give up? How much cost do you invest? And then there's also safety issues with using high temperature and high pressure systems.